Hello everyone, my name is Sarwood from KAIST. In this video, I'm going to introduce a quantum device called Quantum Tunneling Field Effect Transistor or TFET. Firstly, let's get familiar with the function of the transistor. A transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. It is composed of semiconductor material usually with at least 3 terminals, which are source, drain, and gate terminal for connection to an external circuit. It is very useful in many applications as a part of integrated circuits, including the computer we are using. A field effect transistor uses an electric field to control the flow of current through the device. Thus, it is named for an electric field that has an effect on the transistor. In the FET, the current is usually flow between the source and the drain terminal, while applying a voltage between source and drain. The region that current is flowing is called the channel region. This current is then controlled by applying the voltage between the gate and the source terminal. This voltage induces the generation of an electric field within the device, and by controlling the generated electric field, we can control the flow of the current through the device. To summarize, source-drain voltage is used to push the charge carrier within the channel region, and gate-source voltage is used to control the flow of the charge carrier within the channel region. In quantum tunneling field effect transistor, the technique of quantum tunneling is presented to fulfill the role of the transistor. Let's go back together and understand what quantum tunneling is. Imagine that we have an electron with some of the energy moving toward the energy barrier. In the classical picture, an electron would bounce back from the energy barrier if its energy didn't exceed the barrier height, so that electron can't pass through the another side of the barrier. Imagine the situation like you cannot climb the mountain and go down on another side if you don't have enough stamina. In fact, we can't treat electrons like us climbing a mountain, as electrons are very teeny tiny. In this size, a quantum picture is needed to explain the phenomenon. As we treat electrons like waves instead of being particles, electrons do have a finite probability of passing through the energy barrier despite of the barrier height. With the use of the Schrödinger equations and some continuity conditions between each interface, the probability or the transmittance of the electron can pass through the barriers is being calculated. After a long derivation, the transmittance can be approximated as this equation. In this equation, T stands for transmittance, E0 stands for the energy of the electrons coming to the barrier. V is the energy of the barrier. In our case, the barrier energy is higher than the energy of the electrons, so V is greater than E0. And A is the half of the thickness barrier. Frankly speaking, the thickness of the barrier is 2A. From here, if we increase the thickness of the barrier, the exponential term will be decreased. Thus reduce the transmittance value, or in another term, lower the probability that such a tunneling event might occur. So, how can we implement this phenomenon in an application used as a transistor? Imagine that before applying the electric field, the energy barrier is very thick. There is a really small chance that the electron can pass through this barrier. This can be suggested as an off state. Then, what happened during the on state? If we manage to reduce the barrier thickness down during the on state, the probability that electrons can slip through it will be increased. This controlling ability is a fundamental concept to understand the quantum tunneling field effect transistor. Let's first look at the component of the quantum tunneling field effect transistor. It consists of a highly doped P region and a highly doped N region, with an undoped or intrinsic region in between, and are called PIN diodes. There are two types of tunneling field effect transistor, which are N tunneling field effect transistor and P tunneling field effect transistor. In an N tunneling field effect transistor, the P-type region acts as a source region, while in a P tunneling field effect transistor, the N-type region acts as a source. The underlying mechanism of these gated PIN diodes transistors was shown to be band-to-band tunneling or interband tunneling. For this reason, the device is called a tunnel field effect transistor. The tunneling field effect transistor operating principle is the modulation of the potential in the device, enabling or disabling tunneling from the valence to the conduction band. As same as the quantum tunneling principle, the efficiency of band-to-band tunneling depends on the tunnel distance, which is defined as the distance between the valence band and the conduction band. The band-to-band tunneling generation rate is exponentially dependent on tunnel distance, as we see in this relationship, where L0 is a characteristic of length for the given semiconductor material. Same as quantum tunneling, if we increase the length of the tunnel distance, the band-to-band tunneling generation rates will be decreased. Let's firstly look at the off state of the device. In the absence of any field effect from the gate, the tunneling field effect transistor behavior resembles that of the PIN diodes, and the tunnel distance is large and proportional to the length of the intrinsic region. If we apply the potential on the gate, what will be the changes within the energy diagram? In the intrinsic region, in the semiconductor right under the gate dielectric, the gate electrode exerts gate electrostatic control over the potential energy at the surface and causes the band bending of the intrinsic band diagram in the downward direction. For very high gate bias, the surface potential and band bending will exceed the sides of the band gap, and a path from the valence to the conduction band will emerge near the source interface. The tunnel distance is now much smaller than the length of the intrinsic region, and a dramatic increase in the band-to-band tunneling occurs. Further increasing the gate bias will further decrease the tunneling distance and increase the drain source current as shown in the graph, in which IDS is the drain source current and VGS is the gate source voltage. The tunneling field effect transistor belongs to the family of so-called steep-slope devices that are presently being examined for ultra-low power electronic applications. Because of their low off currents, they are perfectly suitable for low standby power logic and low power applications, which are functioning at moderate frequencies. Such applications are electronic digital switch, memory device, ultra-low power specific analog integrated circuits, and low power SRAM. This is the end of the introduction. I hope you understand the basic principle of the tunnel field effect transistor and see how quantum chemistry can be applied in our daily life. Thank you for watching.